My name is Gwansuk Kang from Stanford University. The title of today's talk is Identification of the HIFU Focus using 3D Passive Acoustic Mapping with a Rotational 2D Linear Array Probe. It's about the 3D visualization of the HIFU focal spot. HIFU technique has achieved numerous successful cases based on the precise targeting and monitoring techniques. This slide shows a typical HIFU beam pattern formed in a homogeneous medium and was calculated using a simple life acoustic simulator. In general, the HIFU focal point is displayed on the monitor of the HIFU device. The manufacturer provides this geometric information. However, the situation changes when the ultrasound beam is transmitted into the human body. Unfortunately, we were unable to measure the actual acoustic field in the human body with the current measurement techniques. Instead, we performed the numerical simulation of acoustic propagation in a digital human phantom. The digital human phantom includes various human organs and has both mechanical and acoustic properties, enabling more realistic simulations. Over the past few decades, many researchers have made this technology possible for precise targeting. However, the presence of a heterogeneous medium makes complicated interactions due to the mismatch of acoustic properties. For these complex physical phenomena, the hyperfocal spot can move from the designated location. In the digital human phantom, the beam pattern becomes distorted, unlike the theoretical beam pattern shown in the previous slide. This means that the hyperfocal point can move from the geometrical focal point to another location. The beam pattern changes depending on the acoustic propagation pathway, even if the hyperfocal spot targets exactly the same location. In this case, the focal zone is divided into several parts and the peak position also shifted. We tested under various conditions to monitor how the focal zone changes. For comparison, this slide shows the focal zone in 2D and 3D. For the reference cases, focal zone formed a pretty clean three-dimensional oval-shaped board. However, if you look at the beam pattern in the digital human phantom, it seems different. The focal zone is split into several parts, resulting in several focuses or long stretches. It is also formed at a different location from the geometrical focal point. It suggests that the focal zone can be distorted in 3D dimensions. This was a critical issue from the early stage of the HIFU surgery. Currently, HIFU treatment planning and real-time monitoring are performed by two primary imaging modalities: magnetic resonance imaging and ultrasound imaging. The ultrasonic-based method has the advantage of good cost efficiency, excellent temporal resolution, and is relatively unrestricted than MRI-based method. The structure of the ultrasonic-based method generally has a hole in the center of the HIFU transducer. An ultrasonic probe is installed in the center and conformally aligned with the hyperfocal zone. Therefore, the monitoring boundaries are also limited to a two-dimensional ultrasound imaging plane. As you can see from the simulation result, the focal zone can be distorted in 3D space, not only ultrasound imaging plane. Therefore, this study aims to visualize the focal spot in 3D space using a conventional ultrasound system. This figure shows a conventional ultrasound-guided focal spot monitoring method. The HIFU transducer and ultrasonic probe are comfortably aligned. The monitoring boundaries are limited to the ultrasound probe imaging plane. The ideal way to overcome this limitation is to use a 2D array probe. However, 2D array probes are not readily available because of difficulties in the manufacturing process and the requirement for specialized system. To address this issue, we proposed a 3D passive acoustic mapping method that implemented 2D arrays by mechanically rotating a 1D linear probe. 2D PAM using a rotational 2D array has not yet been demonstrated to the best of our knowledge. In this study, we performed a numerical simulation to generate the raw RF data scattered from the medium using the K-wave acoustic simulator. First, we considered the distribution of elements. Simply rotating the 1D linear probe from the area where the element overlapped. These overlapped elements act as a weighting factor for the signals. We chose a Fibonacci spiral structure. The position of each 2D array element can be obtained by rotating the 1D linear probe and selectively activating the elements. A total of 64 channels were used in this study. Conventional delay and sum beamforming was used to reconstruct the 3D PAM with the 64 channel signals. For the validation of the proposed method, we performed a test with a point source at several locations. A point source generates a pulse of 1.5 MHz and 15 cycles at 35 mm from the probe. The signals were acquired repeatedly while the probe rotates from 0 degree to 179 degrees. Here are the results. The top is the conventional method and the bottom is the proposed method. The red arrow indicates the location of the point source. The conventional method can only obtain a one-side 2D PAM due to the limitation of the fixed linear probe. Since the probe rotates in the proposed method, it overcame these boundary limitations to enable 3D PAM reconstruction. You can see the clean oval-shaped ball in the center in top, side, and front view in the proposed method. We moved the point source 10 mm down along the vertical axis. The conventional method reconstructs the point source as if it was in the imaging plane, even though its position was out of imaging plane. On the other hand, the proposed method found its location accurately in the top, side, and front view. We rotate the point source 30 degrees from the previous position with respect to the vertical axis. The conventional method shows similar result to the top view of the proposed method. After scan complete, in the proposed method, the location of the point source at the level of -6 dB is shown in 3D space. This is for 6 degree rotation. This is for 90-degree rotation. In this case, the point source is located on the imaging plane of the conventional method. Therefore, these are reliable prediction results in both methods. In some cases of the conventional method, a pseudo acoustic source appeared as if the point source was on the imaging plane, even though it was out of imaging plane. On the other hand, the proposed method finds it well in 3D space. For the HIFU pulse, we model the hypertransducer and the sphere mass. The mass has a sound speed slightly higher than the background medium. sound speed was limited to a range not exceeding the maximum range of sound speed in the human organs. We compared 3D PAM with the beam pattern, which is ground truth. There were no significant changes in the focal position, even though the sphere mass was placed. However, the focal zone was slightly upward of the center on the top view, and it was similarly inclined downward to the right on the front view. The proposed method finds the focal zone close to the beam pattern in 3D space. Now summaries. We have proposed 3D passive acoustic mapping method by rotating a conventional 1D linear proof. The proposed method can visualize the distribution of the acoustic scattering intensity in 3D space. The proposed method can implement in a conventional ultrasound system without the modification of the electronics or ultrasonic probe. However, this method requires additional rotating mechanism. Thank you for your attention.